In the last class, we looked at the concept of an isomorphism, which was our ability to essentially rearrange the graph to map into another graph. So the two graphs were essentially the same, just different kind of orders of how they were named and numbered. As we move to real networks, complex networks where they've been sampled and represent real processes and perhaps two different processes, but you'd like to see similarities across them, the idea of an isomorphism just kind of goes out the window. And so what we need is an ability to do what's called network alignment, which is to find some vague mapping between nodes that highlights structural similarities between two graphs. And there's two main ways of doing this. You can either do this locally or globally. When you do this locally, you could possibly end up with mapping maybe two nodes to the same node in the second graph. And so oftentimes you'd get scenarios where your mappings may overlap. But it does end up becoming an easier problem when you try to do local mappings. And so globally doing this is a little bit trickier, but that it kind of guarantees that you don't have these overlapping areas. And it really boils down to two steps, which is figure out some way of computing a number, a similarity score between all nodes. So this would be all the nodes in graph 1 and all the nodes in graph 2. You'd identify all the similarity scores between them. And then in some ways, decide a mapping. And so oftentimes you might do this greedily, which means you just take the best similarity and assign those as being matched together, then take the next best and the next best and so on. Another option, because greedy doesn't necessarily guarantee optimal performance, is to try to use some sort of black box solver in order to optimally select a mapping that matches the most similar nodes. And so similarity, what do we mean by similarity here? Similarity could mean a number of different things. In the literature, if you're just using solely based on graph structure, we see a number of different ways that people do this. One of the most popular ways, and it's given by the name, is to actually go ahead and compute similarity scores the way that you would based on regular equivalence, and that would indicate a good match. And that's essentially this idea that if the neighborhood around a node is similar to the neighborhood around another node, those two nodes might be matched together, or at least have a high similarity score. And then in this class, we're also introducing this notion of a graphlet, which is a small subgraph. And so if the graphlet neighborhood around a node is similar to the graphlet neighborhood around another node, then you could imagine a similarity there. Now, when you're dealing with real networks, it's often the case that you have other information, perhaps node properties or attributes, and these could even be built into the similarity score. So you can imagine that if you had an organizational hierarchy, that you might have the titles of each person, like the role that they play in that hierarchy: manager, engineer, vice president. And so that may also help you identify this alignment by identifying similarity scores that not only take into account the graph structure, but also some of these node attributes. So once we have a mapping, which is what this f function does, it takes in nodes. These is the vertex set of graph 1, and it produces the corresponding vertex in graph 2. So once you have this mapping, the question is, how good is this mapping? And so here there's a lot of formulas here, but let's break this down and we'll see three different main ways that people use to evaluate the mapping. So if we have two graphs, G1 and G2, with vertex set V1 and V2 and edge set E1 and E2, then we're going to assume in general that these two graphs could be of different sizes, but we'll always select G1 to be the smaller graph, the one with the fewer nodes. And so that means that when we operate the mapping F on the vertex set V1, we get a subset of the edges of V2. Okay, so if V2 is bigger, if G2 is bigger, it has more vertices than the first graph, then when we map these nodes from V1, we may get something that is, we're only mapping, say, 10 nodes. If G1 has 10 nodes and G2 has 12, then there are going to be 2 nodes that are left out. And so for that reason, we have this subset. So this V2 tilde is the set of vertices that have been mapped by this function f based on our alignment. So remember, f encodes which node is mapped to which node is most similar to that node. And so we're also going to define this G2 tilde, which is the induced subgraph. So the induced subgraph is the selection of edges such that they are between the nodes that are mapped by F. So remember, we're taking a subset of the vertices, V2 tilde, and we're going to keep the edges that are between these nodes. And so we can define that here. So if there is an edge between U and V in the second graph, so the second graph already has this edge between U and V, and if U and V are mapped from V1, so they're part of the edges, or sorry, part of the nodes that match the nodes from V1 using this function f, then that means that we keep that edge between U and V in the induced subgraph. All right, so now we're prepared to talk about some different ways to evaluate this mapping. And so we're going to introduce one more notation, your favorite thing. So this f is really a function that operates on vertices, but we're going to use this kind of not quite correct notation, but I think it's intuitive, which is say we're going to operate f onto an edge set here. And so what we mean by this is we mean that we look at the edges in the first graph, and those edges are going to be connected to nodes. So for example, these edges which are in the first graph are defined by 2 nodes, U and V. So that U and V, if those U and V are actually mapped by F, so it means that they actually exist so the nodes exist in the induced subgraph, but that this whole phrase says that the edge is also induced. So this essentially means that there was an edge in the first graph, and there is an edge in the induced subgraph. And so that means that we're matching not only those nodes, but those nodes have an edge between them in the first graph, and they also have an edge between them in the second graph. And so that's kind of how many nodes we get correct. So that's the number of edges that we map correctly. And notice that the number that we map correctly is always going to be less than the total number of edges that we're matching. And so for that reason, we just take this fraction, and it tells us the fraction of edges out of the first graph that we map correctly. Now the problem with this is that if we have 2 graphs, it's not clear that the first one should definitely denote the quote-unquote true graph. So we could be missing edges in the second graph, and so it's important to take those into account. So what if we consider the opposite, which is we keep the same numerator, but we divide by the number of edges in the induced subgraph of the second graph. And so again, this is always going to hold because this is the number of correct edges and this is the number of total edges. And so this now accounts for graph 2, but doesn't keep in the the number of edges that were originally in graph 1. And so we get down to this symmetric structure score, which still keeps the number of correctly mapped edges up here, but now we include both of these terms, essentially a penalty for missing edges in the first graph, a penalty in missing edges in the second graph, in the induced subgraph, and then we subtract away the ones that we get correct. So you have to get a completely perfect matching in order to attain a score of 1 in this case. So this is a way that you can include both essentially missing of edges in G1 and G2, but still get a score that kind of tells you how well you're doing by mapping those edges. And so we mentioned before you could evaluate or assign this mapping F from the similarity scores. That was what we talked about on the previous slide. Another way that the optimization techniques do, and these are going to be black box optimization that you just essentially throw it at a problem. And so these sometimes will just take this score and try to optimize this score directly based on changing what the function f is. So that's another way to assign, actually build an alignment mapping. So that last slide was a little bit detailed. So let's take a look at a very simple example. So we have G1 here, and it has nodes A, B, and C. And I have graph 2 here, and it has nodes A prime, B prime, C prime, and D prime. And I've labeled these to be suggestive that we are selecting a mapping that f of A is A prime, f of B is B prime, and f of C is C prime. And notice that G2 is bigger. It has one more node, and it's D prime that's not being mapped. So with this mapping, so we're going to see that there's going to be probably a better mapping in this case, but in this mapping, let's evaluate the proper performance of this. So A, B, and C are mapped to A prime, B prime, and C prime, and so the inducement graph, this is our G2 tilde, looks something like this. So this D prime is not in this graph, and that's why we don't keep that edge there. So we're only keeping edges that are between nodes that are in the induced graph, in this subgraph. So we have, so notice that we have 2 edges in G1, and we have 2 edges in the induced subgraph. Now, even though it looks like the same structure, notice that A is getting mapped to A prime, and A is out here on the leaf of this Y structure, this V structure, and in this graph, in the induced subgraph, it's in the middle, so it's at the vertex here. So they play different roles, and so the alignment is not going to be as good as it seems, even though they look like they're the same structure. And so we take a look at the number of edges that we get correct. So in the original graph, between A and B, there is this edge. And so we take a look to see if that edge is still in the mapped graph. So A prime and B prime, and there is indeed an edge between them. So that is the edge that we get correct. So that's this edge right here between A and B, or A prime and B prime, and that's what is given by the numerator in our edge correctness. So that's the edges that we get correct. So if we look at the original graph again and we look at B to C, there's an edge between B and C, but if we look here between B and C prime, there is no edge here, and so that is an edge that is in G1, but not in this induced subgraph of G2. Similarly, there is no edge between A and C, but there is an edge here between A prime and C prime. So that's an edge that we miss in the second graph. So if we were to evaluate our 2 scores, this is the numerator in all of them, and so the size of that is just 1. So in the first case, it's just 1 edge that we got correct out of E1, the number of E1 edges, and so we get essentially half of them correct. In the second alignment score, we use this as the denominator, so that ends up being the same fraction, 1/2. And then if we wanted to evaluate the last score, the symmetric score, then we would take one edge that we got correct over two edges in G1 plus two edges in the induced subgraph of G2, and then subtract away the number that we got correct, which is 1. And so that leads us to 1 over 3. So those are examples of how you might use these symmetric scores or the similarity scores in order to determine how well this mapping works. And again, in this particular graph, you can imagine that if you picked a different mapping, for example, A goes to B prime, B goes to A prime, and C goes to C prime, you would get a better alignment score, in fact. And so that would tell you that that other alignment is much better.